Good morning, everyone. Today I'll be presenting our study on predictive modeling of osteoporosis and the effect of BMI on femur fracture risk using COMSOL Multiphysics. The study was conducted by a team of researchers, including myself, Alina Kamal, along with my co authors, Minahil Kamal, Mashal Fatima, Syed Mudassir Hussain, Jawwad Rahman, and Sathish Kumar. Our objective was to explore the relationship between osteoporosis, BMI, and femur fracture risk through computational modeling. Let's dive in and discuss the insights we discovered. Osteoporosis is a metabolic disorder that weakens bones, increasing the likelihood of fractures. It is a significant global health issue affecting over 200 million people, and it's often called the silent disease because symptoms typically don't appear until a fracture occurs. By 2050, hip fractures in Asia are projected to rise sharply, underscoring the importance of research on osteoporosis and fracture prevention. Our study specifically focuses on femur fractures, a common issue in osteoporosis. The main goal of our study was to evaluate the risk of femur fractures in osteoporotic patients across different BMI levels. We used COMSOL Multiphysics to simulate and analyze stress points in the femur under these varying conditions. This research is particularly important as it provides insights into how BMI, a commonly used measure of body composition, impacts bone health and fracture susceptibility in patients with osteoporosis. Body mass index, or BMI, is a measure of weight relative to height and is widely used to classify body weight categories. Higher BMI is generally associated with increased bone density, which can be protective. However, for osteoporotic bones, high BMI may contribute to increased stress, potentially raising the risk of fractures. Our study examines this dual impact of BMI on both strength and fracture risk, especially in femur bones affected by osteoporosis. To investigate the influence of BMI on fracture risk, we used COMSOL Multiphysics for finite element analysis or FEA. We imported a 3D CAD model of the femur bone simulating both healthy and osteoporotic bone conditions. By applying load conditions that mimic body weight, we were able to observe stress distribution patterns across the femur, which helped identify areas at higher fracture risk. Here we compare a healthy bone's material properties to an osteoporotic bone's. This comparison is crucial for understanding how bone density and structural integrity are affected by osteoporosis. For a healthy bone, Young modulus is 16.5 gigapascal, indicating a high level of stiffness and resistance to deformation. In contrast, an osteoporotic bone has a reduced Young's modulus of 11.5 gigapascal. This lower value reflects the weakened structure of osteoporotic bones, making them more susceptible to bending or fracturing under stress. The Poisson's ratio measures the bone's elasticity. A healthy bone has a Poisson ratio of 0.43, while an osteoporotic bone has a lower Poisson's ratio of zero point 0.2, showing a diminished ability to distribute loads evenly, increasing the likelihood of localized fractures. Density is also significantly reduced in osteoporotic bones. Healthy bone density is approximately 2000 kilograms per meter cube, while osteoporotic bone density drops to 800. This reduction in density leads to greater porosity and fragility, further increasing fracture risk. The data illustrates why osteoporotic bones are more prone to injury under load bearing conditions, especially in weight bearing bones like the femur. This slide shows how we applied simulated body weight loads on the femur head to analyze stress distribution. On the left, we see the load applied at the top, representing weight bearing at the hip. The right side shows the distal end fixed, mimicking knee joint stability. This setup lets us observe how stress is distributed along the femur, helping identify areas at high fracture risk, especially in osteoporotic bones. Finite element analysis, or FEA, is a powerful tool in engineering, allowing us to examine how structures respond under stress. In our model, after defining the material properties of bone, healthy, and osteoporotic, the model was then subjected to meshing to increase the accuracy of our analysis, and we simulated load conditions by applying forces to the femur head. Our analysis revealed that high stress regions are primarily located in the femur shaft and head. While higher BMI generally correlates with increased bone density in osteoporotic conditions, it also leads to localized stress. This increases the risk of fractures. Essentially, for patients with osteoporosis, the added weight of a high BMI creates a paradox. It strengthens the bone in some ways, but also raises the risk of fractures in specific areas due to concentrated stress. These findings reveal a complex relationship between BMI and fracture risk in osteoporotic individuals. While higher BMI is often considered protective due to increased bone mass in osteoporotic bones, it may actually increase fracture risk by concentrating stress. These insights are clinically relevant as they suggest that BMI management should be considered part of a comprehensive fracture prevention strategy for patients with osteoporosis. In conclusion, our study emphasizes that BMI influences bone health in osteoporotic individuals in a dual manner. While it generally increases bone density, it also raises fracture risk due to stress concentration. In the future, we aim to refine our model by incorporating advanced fracture mechanics and clinical imaging data. Collaborating with medical professionals will allow us to validate and further enhance the predictive accuracy of our model, making it more useful in clinical settings. Thank you for your attention. I hope this presentation has provided valuable insights into how computational modeling can help assess fracture risk in osteoporosis. I welcome any questions you may have, and please feel free to contact me for further discussion if you'd like.